Now let's start on the introduction of these systems. So we are starting our journey now. We started from introduction. By the end of this particular session, you should be able to define different types of systems, and then we will analyze also the relevant mathematical background for dynamic system. Okay, in short, any entities actually is a system. By definition, system is a thing that will respond to any input given to it. Any entities that will respond to any input that is given to that entity, that is system. And system can be in any form. It can be in a form of physical system, biological system, economic model, or anything. One example of an economic model, perhaps a stock market. If you look at the stock market, any situation, let's say political situation, will influence the stock market, and then it will influence the stock price, let's say. Okay, so that is also a system. But as an engineer, we are more interested to mechanical system. So let's take a look of one real world example of a mechanical system, a vehicle, let's say your car. A car by itself is also a system. Your car is a system, and your act in pressing a gas pedal of your car is an act of giving an input to the system. When you press the gas pedal, the car will accelerate. It will run faster. So the response, the output of your car is the acceleration of your car. You have a system, your car, you give an input by pressing a gas pedal, the car will respond by moving faster. So that is an example, simple example of a system. By definition, in general, system can be classified into two different types of system. The first one is a static system. This is the simplest type of a system. A system is said to be static if the output will only depend on the input at the present time, at the current time. So the response of a static system will immediately respond to the current input. The second type, the dynamic system, the behavior is slightly different. The output is dependent not only to the current input, but it also depends on the past input and sometimes also to the past output. Okay, so in dynamic system, the response is not only depending on the current input. Perhaps it's not clear yet, but in the next few slides, I will give you an example of these two different types of system. But one thing that you might need to highlight, the typical characteristic of a dynamic system is simply the response will vary in time, even if you give a constant input. Okay, I will give you an example of these two different types of system. I still remember when I was in elementary school, when my teacher tried to teach me the mathematical concept. She gave me an example of what she called as a function machine. So if you look at this, she asked me to imagine a machine where the machine will add anything that is given to the machine by 3. So if I give 2 to this machine, the machine will give an output of 5. If I give 3, the output will be 6. So in this machine, basically, the relationship between input and output is represented by algebraic equation, by algebraic operation. 2 plus 3 will be 5. So it's just simply like As an example here, if you look at this animation, the blue one is the input. So if I give a constant input of 1 to this machine, the machine will give an output of 4. Just 1 plus 3 equal to 4. So the red dashed line is the output. So it's just simply like that. But again, the operation in this machine can be any algebraic equation, and it can be summation, multiplication, subtraction, or division. Doesn't really matter. Even if I give a non-constant input, let's say if I give a sinusoidal input like this, the output of this machine will just simply add it by 3 of the input. So the output, the red dashed line, is responding immediately to the input. When the input is 1, the output is 4. When the input is somewhere here, I don't know, probably this is 1.6, the output is 4.6. So the output immediately responds to the input. That is a typical characteristic of a static system. Why? Because the relationship between input and output, again, is represented by simple algebraic operation. Now let's take a look on the second types of the system. In dynamic system, the relationship between output and input is represented by differential equation. It's not by a simple algebraic equation. These are the two examples of mathematical representation of dynamic system in which the relationship between input and output is represented by differential equation. So you can consider here y is an input probably and x is the output. So as you can see here, the relationship between input and output is represented by differential equation. Owing to the concept of this function machine, so I will draw it here again, a function machine, but the relationship between output and input is represented by differential equation. Now let's take a look on this case. I will give a constant input to the system here, to this dynamic system, the constant input of 1 here. But because of the nature of this differential equation, the response, the output of the system, depends also on the past input. In such, the response of the system will not follow the input immediately. If you look at this, it takes time for the response x to respond to the input. So in other words, I can say the response will vary in time, even though at the end, after some time, the response can follow the input, the output can follow the input. Okay, as you can see here, after some time, the output can follow the input. When the input is constant, the output is also constant. But in overall, in time, the response will vary in time. The output will vary in time. Similarly, if I give a non-constant input, let's say I'm giving a sinusoidal input to the system, the response of the system will not follow the input immediately. It takes time for the output to follow the input. So at the beginning, it doesn't look like sinusoidal, it doesn't look like the input, even though after some time, the output will behave similar to the input. But in general, it takes time for the output to follow the input. In other words, I can say again, the output will vary in time. Okay, so this is a typical characteristic that differentiate dynamic system to a static system. Having the definition of the dynamic and static system, I have an example here, and then after you look at this animation, I want you to decide whether the system that we are talking about here is a static or a dynamic system. So what the system that I was talking about is a weighing scale. So imagine you have a weighing scale to weigh your body weight. So what will happen here? There is a kid here. This kid is trying to weigh his own body weight. Let's take a look on this animation. So this boy is going to weigh his body weight. So he knows when he is trying to weigh his body weight, his weight is 24 kilograms. So what he is doing now, he will jump to the weighing scale. Assuming that the body weight of this boy is constant during the entire measurement, well, we can consider it as constant. He's not eating or drinking during the measurement, so we can consider that the body weight is constant. Assuming that, so this boy is giving a constant input to the weighing scale. Weighing scale is a measurement system, so essentially the weighing scale is a system. So the boy is giving a constant input of 24 kilograms to the measurement system. And what will happen to the weighing scale? The weighing scale will respond accordingly. How does the weighing scale respond? The dial of the weighing scale will start to move. Okay, so the output of this weighing scale basically is the motion of the movement of the dial of the weighing scale. The input is the body weight of the boy. The output is the dial position of the weighing scale. Okay, so you have the input, you have an output. At this point, I want you to answer whether this system is a static system or a dynamic system. You can pause this video for a while, think about it, look at the definition, and then if you are ready to answer, you can continue this video. Now, looking at the input and output, as I mentioned before, when the boy is jumping to the weighing scale, he's giving a constant input, 24 kilograms, which is his body weight. And the output is the location of the dial, position of the dial. If you still remember how the dial moved after this boy is jumping on the weighing scale, the dial is wiggling, right? At the beginning, the dial is wiggling until, I don't know, a few seconds. The dial stopped at one specific scale that corresponds to the body weight of the boy. So looking at this, the response, the output of the system, the output of the weighing scale, which is the dial location, is varying in time. The input is constant, the output is varying in time. What does it mean? This means the weighing scale is a dynamic system. I have a second example here. It's a light bulb. So how a light bulb works, of course you know. When I switch the electric switch of this light bulb, the bulb will start to light up, right? So again, if I switch it on, the bulb will light up. So looking at the system, then the input to the system basically is the voltage. The action of switching the switch is basically giving a voltage input to the light bulb. Light bulb is the system in our case here. So I'm giving an input of voltage to this light bulb. Let's say if the voltage is 220 volt, I'm giving a constant constant voltage to the light bulb of 220 volt, correct? So the input is again constant 220 volt. And what is the output of this light bulb? Definitely, the output is the light intensity. So when I start to switch on the light bulb, I have notion the light bulb is instantly light up. Okay. Now the question is the same like the previous one. Is the light bulb a static system or a dynamic system? You can again pause this video for a while, think about it, and you can answer whenever you are ready. To answer the example of a light bulb, some of you might have a notion that the output of this light bulb responds immediately to the input. When I switch on the light bulb immediately light up, right? If this present the voltage input, you might say that this is the light intensity, which is the output of the light bulb. You might have notion at this point that the light bulb is a static system because the output responds to the input immediately. But now I have a video here. The video of the light bulb after I switch on the light. But this video I will run it in a slow motion, in a very slow motion. I think about 100 slower than a normal rate of a video. So when I click the switch, if I run this video in very slow motion, the filament of the bulb will start to burn. But if I run this video in very slow, you can see that the light bulb takes some time to burn the filament. So what does it mean? This means the system, the light bulb, also takes time to respond to the input. But the response time is very fast in here, perhaps in microsecond or millisecond. But anyhow, the system takes time to respond to the input. So if I plot the output, the light intensity in time, but I take it in a very slow scale, if you look at this time scale, it's very slow. The output of the light intensity also varies in time. Okay, so essentially again then, light bulb is not a static system, it is also a dynamic system. One question then from these two examples: can you give an example of, in a real world, of a static system? I cannot give an example of, in a real world, of a static system. Why? Because all systems in nature essentially are dynamic. There is no static system. Static system only exists in a piece of paper or only exists in a theory. Okay? So since all of the systems are dynamics, we will focus this course on dynamic system.